Okay, hi. This is the video on, and I want to speak today, or in this video, on about the loaded voltage divider. So what I've drawn here first is an unloaded voltage divider, and you recall that the equation that describes the output voltage in terms of the input voltage and the resistors is just V times the resistor across which you are taking your voltage. That would be in the numerator, and in the denominator is the sum of the two resistors. So that is the standard voltage divider equation. This is, though, an unloaded voltage divider situation, because as you will find when you do your pre-lab, the idea of this equation depends on the fact that R1 and R2 are in series. Well, when R1 and R2 are in series, then what must be true is that the current in this branch here, going out and coming back in here, some I, must equal 0. There's no other path for the current to take. Once it comes through R1, it must all go through R2 in order for R1 and R2 to be in series, and R1 and R2 being in series is essential to the development of this equation. So if this I here is 0, that means that we have an unloaded voltage divider. What do I mean by that? What I mean is that no current is being demanded of this voltage divider, and so it has to play into basically an open circuit, which is what I'm showing here with these two open circles here. That's where a load would be connected if there were a load, but there isn't. If a load were connected to these two open circles, then this I would not be 0 anymore. It would be some other current value, and all of a sudden R1 and R2 are no longer in series. So what happens when we have a loaded voltage divider? Okay, so what I'm going to do then is I'm going to say, well, I'm going to put a load on this. I'm going to put a load on this voltage divider, and the load will be in the form of another resistor. So I'm going to call that resistor R sub L. So now, what do we have? We now have R2 and RL in parallel. The parallel equivalent of them is in series with R1, because all of the current going through R1 must go through either R2 or RL, one or the other, and R2 and RL can be replaced by a parallel equivalent resistance. So now what does our voltage divider equation look like? Well, instead of R2 over R1 plus R2, now the output voltage equals R2 in parallel with RL over R1 plus R2 in parallel with RL. All of this multiplied by the input voltage. So this is now the new voltage divider equation, and of course we know what the parallel equivalent resistance is. It's the product over the sum, right, for two resistances. So this would be R2 RL over R2 plus RL over R1 plus R2 RL over R2 plus RL. And that, of course, if you multiply both sides by R2 plus RL, then that gives us R2 RL over R1 R2 plus RL plus R2 RL. Whoops, I forgot the V here. Let me put the V in, and there's a V here. A little more times V here. And I'll There. Okay. So now you can see that what do we got? We have R times R in the numerator, and then R times R in the denominator, and so the ratio is dimensionless, as you would expect it to be. Voltage on the outside of the brackets equaling voltage on the left side of the equation. So now this is our new equation that describes a loaded voltage divider. And you can see again, it is a function of the two resistances plus now the load resistance, whatever that is, and the input voltage. So this is our new expression for loaded voltage divider. And so the lesson to be taken from this is obviously different from the original voltage divider equation. So you must look for, if you think you may see a voltage divider, you must look for current being drawn after R1 but before R2, a path for current to go. If there is a significant path for current to go between R1 and R2, then you can no longer consider R1 and R2 to be in series. For instance, if you have a resistance here of some kind that is of the same order of magnitude of R1 and R2, I mean, if it's really, really, really big, like 10 megohms or something like that, then you can basically assume that this current will be very small, and you can, within certain limitations, assume that that's still an unloaded voltage divider. So it probably is not a bad idea, at least for a first approximation, if you happen to be playing a voltage divider into an op-amp circuit, an operational amplifier circuit, especially something like a voltage follower, which we will be talking about later on in the course. You can probably still assume that this acts like pretty much an unloaded voltage divider, because an op-amp voltage follower has a very, very high input impedance, and therefore draws very, very little current. So that's the end of the loaded voltage divider video. Thank you for watching.